Now, moving to the presenters that we have today, we will, here I will introduce our first presenter, who is Jinping Zhang. He's a PhD candidate from Imperial College London, and he will talk about a very particular application of machine learning using natural language processing on HPCC. So without more introduction, Jinping, the floor is yours.
Thanks, Fabio, for the introduction, and also thanks for Jessica for the openings. It's great to join the Tech Talk again, and also it's great to share our research at Imperial College Data Science Institute, and really appreciate the support I will get from LexisNexis and also HPC systems on our research. So for today's talk, we'd like to focus on the natural language processing, and specifically the integrating prior knowledge with machine learning models in biomedical natural language processing. So, all right, so the first quick poll question is, have you heard about the phenotypes? So the phenotype is going to be a concept that we're going to go around a couple of times in this presentation. So I will also define this later if you don't know. Okay, so why we need prior knowledge with deep learning? So so prior knowledge in general we may think is a kind of common sense or background knowledge. So it's kind of, I mean, for humans as well, for us, when we learn languages, when we use languages, it takes quite a long time for us from a baby to accumulate the experience or knowledge we need to finally achieve a more complicated communication task, like communicating with colleagues in a smart way, or doing a presentation like this and taking questions. So these are all challenging tasks for humans as well. Not for humans, but also for the computer science. And so what we believe that for machine learning models, for the data we have, we can get, is not only doing feature extractions or statistical analysis on the data itself. It's all very important to consider the background knowledge or the prior knowledge we can get from the real world, so that we can make the decisions more precisely. So in the learning box in the middle, we say there should be a interaction between the perception on the data and also the prior knowledge which we can get from knowledge providers. And there can be two kind of knowledge that we consider in natural language processing. So the first one is the unstructured knowledge. So what is unstructured knowledge? So unstructured knowledge, it can be implicitly contained in a larger corpus. For example, for humans, we read news articles or blogs every day. So it's kind of a lot of textual information we can get every day. And so it's kind of a knowledge we can learn from the materials available online or on books or some on papers. And so it's quite hard before to effectively extract the knowledge from the text corpus and use it for machine learning models. But right now, especially last year in 2019, so we've observed there are lots of works trying to use pre-training techniques to improve the model's performance by using those unstructured knowledge. So it's very impressive performance, and we are also very interested for the trend of this direction. And at the same time is the structured knowledge, so which is explicitly defined by a knowledge graph or biomedical ontology or hierarchy or trees. So those specific knowledge, this specific knowledge has been proven to be effective in tasks that require reasoning or understanding. So for example, if you want to know the author of a book, you'll probably have to search the book first and finding out the connection, the author of the book, and answer that question. So certain simple reasoning or more complicated reasoning that may need those structured relationships between entities. So, in our recent researches from last year, we tried to leverage both structured and unstructured the data as a prior knowledge to improve the deep learning models in natural language processing. So, for example, using the unstructured data, using the structured data, we try to use the large graph for zero-shot task classification, and also for the phenotype annotations on the electronic health record. And for the unstructured data, we use the web page data and design the pre-training techniques for the textual summarization. And it includes both general summarizations on general datasets and also including biomedical literature like from PubMed. And for this specific talk, so I would like to talk more about our research about the phenotype annotation on the EHRs. So the motivation of this work is we observe there are more and more EHRs that are using right now in the hospital, especially at this special moment of COVID-19, that a smart, remote, or electronic way for hospital service or medical services is more and more important right now. So the motivation of this work is whether we can understand the professional and also natural languages in the medical domain with manually predefined biomedical ontology. So for example, so we have the plan test, which is written by the clinicians inside the EHRs. So it is still the most common format that we can see in the EHR, and also most informative way the doctor can store some information. And the thing is whether we can connect the plan test with biomedical ontologies. So for example, the disease code, the phenotype ontologies, or other genomic ontologies. So those are predefined by medical experts. How we can find a relationship between this to structuralize the EHRs, so that later we can use that for other purposes like analysis or diagnosis or treatment, for example. And for our research, we specifically focus on the red boxes, which is finding a relationship between the EHRs and biomedical ontologies. So in this work, we aim to annotate the EHRs with predefined phenotypes. And the EHR is actually a very rich resource of phenotype information. So, what is phenotype? So we use phenotype from ontology named human phenotype ontology. So it's a standardized knowledge base of the phenotypes. So you may think that phenotype is a kind of clinical characteristics of patients, and it is observable by the clinicians, and it can be written by the clinicians inside the clinical notes. And it looks like a hierarchy, so which means that there is going to be primary categories of phenotypes, and then moving on to secondary phenotypes, and then for more detailed phenotype in the hierarchy. And just for example, in the primary level of the phenotype, there are abnormalities of digestive system, immune system, and nervous system, or very general categories. And our work is trying to annotate the phenotypes from the EHRs. And so the reason why we want to do it, want to annotate the phenotype is we're finding out that the patients who are diagnosed with the same diseases in the EHRs could be further classified or subgrouping by the phenotypes. So just for example, like some patients may be diagnosed by headache, but some patients may have very serious headache or serious situation, like the headache is caused by brain cancer or some other severe diseases. But some other patients may have the headache may caused by some slight confusion or caused by other rather slight problems. And in that case, I mean, apparently those two groups of patients should be treated differently, but regarding the disease code, they actually have probably similar disease code, but they should be treated separately. So that's why we're saying that the phenotype information can provide us more indication or more information that we need for disease diagnosis and also for precision medicine. And so that's why we are working right now with phenotypes and designing a model based on the phenotypes. So basically, the data set we're working with right now is the EHRs come from the data set called Mimic3. So it's a public EHR which contains de-identified information about around 40,000 patients. And also at the same time, we're using the human phenotype ontology, or called HPO. It's a standardized knowledge base of phenotype information. So there are over 13,000 HPO terms inside it. So it looks like a hierarchy, as you can see in this diagram. So our work is to propose a novel unsupervised deep learning framework to exploit the supportive information contained in the HPO and annotate the phenotype on the EHR semantically. And we have experiments show the state-of-the-art performance regarding the efficiency and also accuracy. The reason why we try to use unsupervised method is like for clinical area, for the medical area, is the data is quite expensive, especially data with labels. So try to find out whether we can have a very data efficient way without any labels so that we can still achieve some kind of accurate annotation. But right now, after this work, in this year, we are extending this work to have a little supervision, like by using like human in the loop or active learning, to probably improve the performance significantly by very little supervision. But we're still exploring that. But for this work, we focus on only unsupervised methods. And just for example, how the annotation is going to look like. So for example, we have the EHR tags on the left-hand side describing the clinical characteristics of patients. And for example, it describes the blood pressure, CKA, or other kind of phenotype information inside the EHR. And on the right-hand side, there are those are the phenotypes that can potentially annotated on this EHR because this phenotypes are mentioned inside the EHR narratives. And the question is, so one way is we can do it easily by information retrieval, by keyword matching, something like this. But it's quite hard. Like in the EHRs, the doctor may write down the EHR in different ways. So you can't easily define all the rules you need to extract the phenotype. Like for example, like the blood pressure, the doctor may write the blood pressure in hypertension, hypotension, or high blood pressure, or blood pressure is high. So there are lots of different expressions that can describe the same meaning. And so that's why we chose a semantic method. So that, no matter how different the expression is, as long as the context can show this information so that we can detect those phenotype information from the semantics. So therefore, we can formally define this research problem as we have a collection of EHRs, which is represented by the symbol of axis, and then we have the standardized the HPO terms. And for this research, we only focus on the primary category of phenotypes, so which is, you can see in a hierarchy. So from the root nodes, so the first level of phenotypes, there are around 24 of them. So we only focus on the annotation of this 24 general category of phenotypes. And inside the HPO, actually, there are much more detailed HPO available below the general categories. And we use that as supportive information in the training of learning, in the training of the model. But we are not directly annotating on that. We're only annotating the primary category. And so therefore, each EHR can be annotated by either multiple phenotypes, a single phenotype, or even none of the phenotypes. So basically, it's a question of learning the conditional probability, which is whether a specific phenotype is mentioned inside the EHR. So it's a probability between 0 and 1. So 1 means definitely this EHR mentions this phenotype and we should annotate it, or otherwise 0 means this EHR has nothing to do with this phenotype. So basically, it's a binary classification for each phenotype, and because we have 24 candidate phenotypes, so as a whole, it's a multi-label classification of the 24 phenotypes for a single EHR. So our methodology is based on two assumptions. So the first assumption about semantics is we assume the semantics of the general phenotype can be represented by a prior distribution, and the prior distribution of each phenotype should be distinct enough from each others. So just for example, let's just demonstrate it here. So we have an EHR, one EHR HJ, and it can be represented and also generated by a vector. So just like a vector, a semantic vector. And this vector should be a sample from a prior distribution. And the prior distribution of this phenotype should be distinct enough from all the other prior distributions of other phenotypes. And second assumption is we assume the semantics of EHR is a composition of the semantics of phenotype. So which means that the semantic of EHR, which is represented by a Z star, and this star should be a weighted composition of ZJ, and ZJ is also sampled from the same prior distribution of the phenotype, and also the alpha here represents the weight. The weight intuitively means the higher the weight it is, it means that this phenotype plays a more important role in this EHR, or otherwise the weight is 0, which means that this EHR has nothing to do with the phenotype. So just just simple. So therefore, we propose this pipeline learning framework. So we have the textual data on the left-hand side as the input inside the encoder, and then we get the semantic representation in the middle, which basically the weight and vectors I mentioned in the last slide, and then the weight composition with the Z star, and we have another generator to reconstruct the text, and also we have a classifier. So the first thing we need to make sure is in the middle, the Z star in the middle can well represent the semantics of the textual data we have on the left-hand side. So we consider the general textual reconstruction, so which means that we get the Z star from the encoder, and we need to reconstruct the tags from the generator, so that we make sure that Z star contains all the semantic information we need of the tag. So over here, so there's a mathematical equation to demonstrate that we need to maximize the reconstruction probability. But at the same time, so we also have the descriptions or definitions of each phenotype. And this gave us very good indication because that the phenotype description naturally corresponds with phenotype. So which means that we know the ground truth of the weight over here. So besides the reconstruction, we also consider that we should constrain the alpha. So for example, if we gave the description of phenotype J on the left-hand side into the encoder, so the corresponding weight, which is alpha J, should be 1 or as high as possible, but the weight of all other phenotypes, alpha 1 or alpha M or the other alphas, should be nearly to 0 because there's nothing to do with it. So that's the idea. We apply an extra constraint over here together trained with the reconstruction. But more importantly, at the same time, as we assume that the phenotype should be distinct enough from each other, so which means that the vectors representing each phenotype should also be distinct from each other. So therefore, for each of the vectors in the middle, the Z1, Z2, ZJ, and ZM, so all of them should be classified into, should be able to classify into different classes, so that to make sure that their vectors are actually different from each other. So we apply another classifier as a constraint to make sure that the DJ or each of the vectors Z can be classified into the correct classes that the phenotype corresponds to. So these are the loss functions that we are using. But for more technical details, if you are interested, you can check the paper as mentioned on the top of the slide. So for more equations and learning pipelines. So we basically compared two objectives. So one is the efficiency of the model, and then also the accuracy of the model. So we'll basically compare our model with the other current available method, like the OBO and CBO method. All these methods are information retrieval-based methods. So we can observe that they are suffering from the low efficiency, which means that based on the indexing or retrieval, it takes quite a long time for finding the phenotype information from the EHRs. And so, and our method, if we consider only the inference time, so our method is more efficient than all the others. And at the same time, since the large-scale gold standard is not available, so we created a silver standard, which is based on the disease code we have coming from the EHRs. So apply some mapping. So those mappings are human created to create a mapping from ICD to HPO, and use that as a silver standard, and compare with the annotation results from different methods. And we can see our method have the overall highest F1. And so we also tried it on another data set, PubMed. There are around a couple hundred of gold standards, and we also have the highest accuracy on the PubMed. But as we say, so this is all on the primary level of the phenotype. So we're actually working on this to extend it to the second level or even detailed phenotype for all the phenotype annotations. So for this conclusion, is we propose this centralized learning method. So we prove its efficiency and effectiveness, and also we believe that the method can be helpful for disease diagnosis. For the future work, as I said, that we are trying to integrate more data sets from PubMed, and also we're collecting data from elsewhere for biomedical literature. And also we plan to extend it to all the 13,000 phenotypes, which are quite challenging right now, we are facing. And we try to improve the embeddings of HPO, those factors. And also at the same time, we feel like if we want to annotate more than 1,000 phenotypes, the pure antivirus method maybe is struggling on this. So we're exploring methods whether we can apply some active learning strategies to apply some little supervisions on the model so that we can improve significantly on the phenotype annotation. And also the same, we're also interested in the application of this work on the general NLP technique, NLP domain, so which means annotate any given knowledge graph on any given tag. That also would be interesting. That's all. Okay. The second quick 4 questions. So, could you see the framework being leveraged in other types of medical research? So I really appreciate your feedback and suggestions. Thanks.
All right. This has been a wonderful presentation. It's very interesting. So while you take a second and look at the questions from the audience and prioritize those, I'm going to take a second to review your first poll question. And your poll question was, have you heard a phenotype? So from our audience, only a third had heard a phenotype. So hopefully they've got something good from this. All right, let's take a quick peek at the questions. And if you haven't gotten your question in, there still is time, so please go ahead and send those. All right, so our first question is, what is the main challenge of the model? What is the main challenge that the model is facing in future work?
Yeah, thanks, Jessica. So, so for this work, as we are extending the annotation from the primary level to more detailed HPO, so we can see there are going to be explosively more phenotypes we need to annotate, from 200 in the level 2 and 1,000 on level 3 and even more on level 4 and level 5. So we feel like our model currently learning capacity is limited. So it's quite struggling to annotate all the hundreds or even thousands of phenotypes. So that's why one thing is how we can make sure the model still works in the scenario that we need to annotate more than 100 or even thousands of phenotypes. The second thing is the data efficiency is very important because we have very limited gold standard available from the experts. So we need to make sure that we can only annotate probably hundreds of EHRs. Our model should be 100% exploit those information available so that the model can be improved. Yeah.
All right, fantastic. Yeah, it's definitely scale and efficiency are so important. So, all right, a second question. Are there any other NLP tasks that you're interested in and working on?
Yeah, so the phenotype annotation is just one specific scenario or use case that we're applying our models. But at the same time, so like I introduced in the beginning, that we're also working on summarizations on the clinical notes. So for example, the clinical notes, there are the clinician descriptions in the beginning which describe the hospital course, something like that. But they're always at the end there is a discharge instruction for the patient. So we're interested whether we can use the clinical notes in the beginning to generate those discharge summaries. So that would be interesting. So that the doctor there's no need for the doctor to write down the instructions anymore. If our machine can generate in high quality, that will probably going to be very useful.
All right, yeah. Great. All right, so here's another question for you. How would the model perform if it was applied on other biomedical literature data sets like PubMed?
Yeah. So what we can observe from the mimic data set is the clinical notes is quite informal. In the expression, the clinicians write down what they think about or what they observe. But PubMed, like the literature from PubMed or from elsewhere, is actually more formal because those are research papers. So there are peer reviews for this. So it's quite high quality. So you can see there's a quality difference and also some expression difference between the clinical notes and biomedical literatures. So definitely there's going to be a probably different vocabularies or different fine-tuning technologies need to consider in that. So I think we haven't started on working on that, but I think it's going to be important in our next stage work. Yeah.
All right, great. All right, it looks like we have time for one more question, and that is there a published artifact, a journal or a conference paper, for instance, where our audience can have access to your research in more detail?
Yeah, so for this papers and also other papers we have, so it's all available, on the website you can see over here, on my personal website, so you can find a list of those applications and also PDF. So if you are interested, so please have a check and also welcome the feedback. Thanks.
Before we move on to our next speaker, I want to take a quick look at your last poll question, which was, could you see this framework being leveraged by other types of medical research? And 100% said yes. So definitely, it looks like you're on to something pretty exciting here. Thank you so much, Jingqing.